You see it all the time, right? One day, a study says coffee is a miracle cure. The next, it's public enemy number one. It's a lot. So how do we, or maybe more importantly, how do scientists, cut through all that noise to find what's actually true?
That's the big question, isn't it? When a doctor tells you to take a certain medicine or a health agency puts out a big warning, they're not just flipping a coin. There's a really specific, powerful method they use to interpret all this complex information and make calls that can literally affect millions of lives.
And you know what? A toolkit is the perfect way to describe it. It's like a specialized set of tools designed for sifting through a mountain of messy, chaotic information and pulling out that one clear signal that matters. And the name of that toolkit? Well, it's statistics. So, let's make it official. We're going to dive into the science that really powers modern medicine and public health. It's called biostatistics, and I promise it's way less scary than it sounds.
First things first, what even is statistics in general? Just think of it as a process, a system. It's the whole shebang, from gathering the raw data all the way to making a solid, logical conclusion. It's basically the rule book for how to argue with numbers and win.
Now, let's get specific. Biostatistics is just taking that same powerful rulebook and aiming it squarely at living things. So whenever we ask those huge questions like, does this new cancer drug actually work? Or what really increases your risk for heart disease? Yep, you're in the world of biostatistics. Okay, so inside this world, there are two main ways to tackle a problem. You can either just describe what you're seeing right in front of you, or you can use what you're seeing to make a really smart guess about the bigger picture.
And this flowchart here, it shows that split perfectly. You've got descriptive statistics on one side and inferential statistics on the other. They're a team for sure, but they have totally different jobs. Let's break them down.
Let's start with descriptive. The best way to think about this is like taking a class photo. It tells you exactly who showed up that day, what they were wearing, how tall everyone is. It just describes the group you have. That's it. It's not trying to guess about the kids who were homesick or what other classes look like.
And this is so important. Descriptive statistics only talks about the specific group you actually measured. So for these 50 cardiac patients, we can state facts. Their average blood pressure was 145. The range was 120 to 180. We are talking only about these 50 people, nobody else.
Okay, now for the other side of the coin. Inferential statistics. This is where things get really cool. This is like looking at that one class photo and trying to make an educated guess or an inference about the average height of every single student in the entire school. You're using a small piece of the puzzle to see the whole picture.
So, building on our example, we can use our little group of 50 patients to ask a much bigger question. What's the average blood pressure for all cardiac patients in the whole city? Inferential tools let us calculate a probable range. We can say, hey, the true average for everyone is probably somewhere between 141 and 149. We're making a calculated jump from what we know to what we don't know.
And that jump right there brings us to two of the most important ideas in all of statistics. The difference between the massive group you want to know about and the small group you can actually get your hands on to study. So, on the left, we've got the population. This is the big one. This is everyone. All adults with diabetes in the entire country. It's usually just way too huge to study directly. Which is why, on the right, we have the sample. That's the small, manageable group that you pick out of the population to actually collect your data from.
This visual is just perfect for explaining it, right? The population is the whole giant crowd. You can't possibly talk to every single person. So what do? You carefully pick a few people. That's your sample. And what you learn from them gives you a surprisingly good snapshot of the entire crowd. The whole key, though, is that the sample has to be a good representation.
Okay, so we know who we're studying, but what are we actually measuring? The information we collect, our data, it comes in different flavors, different languages, if you will. And we have to know which language we're speaking to analyze it the right way. We call these things variables.
The first big split is super simple. Is it a quality or a quantity? Qualitative variables are categories, like a person's eye color or their blood type. Quantitative variables are straight-up numbers, like their height or their weight. But it gets a little more detailed than just that.
So even within qualitative data, you've got two types. First are nominal variables. These are categories with no particular order. Think gender or occupation. One isn't higher than the other. But then you have ordinal variables, and these have a definite ranking. mild, moderate, and severe disease. There's a clear, meaningful order to that.
And it's the same deal with quantitative or number-based data. Discrete variables are things you can count in whole numbers, like how many times you've been to the hospital. You can't have gone 2.5 times. But continuous variables can be any value in a range. Think height, weight, temperature. And look, knowing this stuff is absolutely crucial because the type of variable you're working with tells you exactly which statistical tools you're allowed to use.
All right, we've covered a lot of ground. Describing versus inferring, population versus sample, and the different languages of data. So now, let's put it all together and see how it works in a real-world example.
Okay, here's our scenario. A researcher is studying adult smokers in a city called Peshawar. Now, they can't possibly talk to every adult, so they select a random sample of 10,000 adults. And they find that 42% of them are smokers. Pretty straightforward. So let's apply our new vocabulary.
First question for you. In this study, what's the population? Who is the researcher really trying to learn about?
Exactly. The population isn't just the 10,000 people in the survey, it's the entire group they want their results to apply to. Every single adult in the city.
Okay, nice and simple. So if that's the population, what's the sample here?
You got it. The sample is that specific group of 10,000 adults they actually talk to. And by looking at the descriptive stats from this sample, the 42% figure, the researcher can then use inferential statistics to make a really good guess about the entire population. See, it all connects.
And that's the whole game. From one small, carefully chosen sample, we can make these powerful, life-saving guesses about a whole population. This is the engine that drives medical discovery. It's how we figure out if a new drug works, what's bad for us, and how we can all live healthier lives. So now that you know the basics of the toolkit, what's the first health mystery you'd want to solve?